This is my presentation about the chapter 2 in the Knowledge Graphs book, which is about the data graph. And this is an outline of some kind of graph data models and the language is used to query them. So in this presentation, Hian Pham and another student named Nam Phương Chen will be the presenter. So this is the outline of our presentation. First, I'm going to talk about the graph models, and the second session is about the some querying method of the graph, which is be talked by Nam Phương Chen. So this is the outline of the first session, the graph models. Firstly, I'm going to talk about the motivation, and then from slide 2 to 5, I'm going to introduce to you some very popular type of graph data models in practical. And finally, I'm going to talk about some kind of other graph data model, and then the graph stores. Okay, so move to the first slide. I'm going to talk about the motivation of data modeling. So considering the running example, which is given in the introduction chapter, where a tourism board used a knowledge graph to increase tourism in the country and then promote new attractions from other areas. So to do this, the board need to store the data about the routes, the events, and so on and so forth. So the board first think of the tabular model. In particular, it is the relational database, and that most of us are very familiar with. And the board begin with the table event, and it has 5 columns, which are name, venue, type, start, and end time of the event. But along with this, the boss is having some troubles, having some issues. What if an event have multiple names in different languages? What if it has multiple venues? And what if it has no start and end time because it is an uh, future event, And the most important thing is that the board want to change the data, want to change the schema over time. For example, add more field, alter the schema of the event, maybe remove some columns and then add more columns. So this kind of altering, this kind of updating can cause really costly remodeling, reloading, and reindexing. So finally, eventually, the board come up with a more flexible schema. And you can see here, the board have 5 elements, which are represented for 5 information here. And all of them are connected by the ID, the event ID. So this is the very beginning of modeling a graph. Okay, so moving to the next one, I'm gonna introduce you to a very popular data graph model, which is the directed at labeled graph. So what it is a directed at labeled graph, sometimes can be called multi-relational graph. It's defined as a set of nodes and a set of directed labeled edges between those nodes. So there are 2 very important elements here, which are the nodes and the edges. Sometimes can be called the chipels. So the nodes, as you can see here, for example, in this image, the urban market or the food festival or the drinks festival, they are all nodes. So the nodes is the elements in the graphs, and the edges is the relationships between them. For example, we have a two assets, bus from Santiago to the city Vina de Mar, and then from the city Vina de Mar to the Santiago. So an edge is defined by the 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 sort node, the target node, and then the relation between them. And in this case, there are two edges of the bus because this is a two direction arrow. So for this kind of way to do, model data, it's really easier to integrate the new source of data. So it's support more flexibility for integrating new source of data compared to the relational database, because as you can see here, all of the informations are represented by nodes and relationships. That means if you want to add more you add more information, for example, the event ID 15, you want to add the host for it, you just add another node and it relations to the event ID 15. You don't have to enter anything in, for example, in the case of the relational database, you need to add one column to the table, and that will affect all the table and affect all the old data. So that would be a little bit dangerous. And as you might know about other kind of data modeling, can also support the same advantage like the XML or the JSON, but it requires data to be organized hierarchically. But in the case of the graph model, it does not require that. So it's much more easier for structure the data. And another thing is that the directed edge labeled graphs also support to represent the cycles and then query them, which is really hard in the other kind of data modeling, for example, the relational database. For example, here you can see from the city Santiago to city Arica and the city Vina de Mar, we have a cycle from these three cities. So this can be represented very easily in the directed as labeled graphs, but it's not in other kind of data modeling. So in conclusion, we have as a definition of the directed as labeled graph. It is a tuple of three sets, V, E, and L, where the V is a set of nodes, the E is a set of edges, and the L is a set of edge labels. Okay, so we move to the next type of graphs, which is the heterogeneous graph. So a heterogeneous graph, sometimes can be called heterogeneous information network, is a directed graph where each node and edge is assigned one type. So what it means is that, as you can see in this example here, instead of represent the Santiago has a type of city, this is a two nodes and one edge. Instead of doing this, we can just simply combine it in one node, and the type of a node is a city. So here we can see the Santiago has a type of city, and this is the type of the node Santiago. So With this way of represent the data, it's easier for you to uh, partition nodes according to their type. So because the nodes have its type, you can just easily partition them and then um, get faster in searching them, in querying them. So this is one of the very uh, significant advantage of this heterogeneous graph. But this kind of graph have limitation. It is that this graph only supports a one-to-one relation between nodes and types. For example, from the previous example, we can see the event ID 15. It has a two type, which are open market and food festival. So this node has two types, so it cannot be represented in the heterogeneous graph because it's a two type. And another node as the Santiago, it has no type. It also cannot be represented in this kind of graph. So it is the limitation of this graph. So in conclusion, we jump to the definition of this graph. This is a tuple of three sets, and one map. We already know about these three sets. And the map small l here is the maps of each node to a label to its type. For example, the map from Santiago to the city. Okay, so we move to another very popular kind of graph, the property graph. So the property graph allows a set of property value pairs and a label to be associated with both nodes and edges. So what it means is that this kind of, if you want to add more information into your graph, for example, if you want to add the information about the um, the company that offer the flight. So with the directed edge labeled graph, all you have to do is that you add more nodes and relationships between them to the graphs. So this will make the graph look a lot complex and um, and quite hard to be looked at like this. But for the property graph, it can resolve this problem very easily. You just simply add a property value pair to the edge or a node you want to add more information about. For example, here we have the flight LA380 is offered by the company name LATAM. And this kind of graph look a lot more simple. This property graph currently prominently used in a graph database such as Neo4j. And this graph can be very easily converted to and from directed as labeled graphs, as you can see in this example here. And also the property graphs offer additional flexibility when modeling more complex relations. As I already said before, a lot of complex relations can be resolved by just adding more property value pairs into the node or the edges. So it will be a lot more flexible than the directed as labeled graph. So the definition of the property graph, we have the tuple of 5 sets and 3 maps, where these three sets we already are very familiar with, and we have these new two sets. The capital P is a set of property. The capital U is a set of values. The small e is the map of an edge ID to a pair of node IDs. The small p is a map of a node or a edge ID to a set of property value pairs. And a small l is a map of a node or an edge ID to a set of labels. Okay, so we move to the next slide, which is about the graph dataset. So commonly, it is often desirable to manage several graphs rather than just one monolithic graph. This is because if you have multiple sources of data, um, you definitely want to separate them because it will be easier for you to control over all of the sources instead of just combine all of them into one source and then um, manage the data from that source. So because of this, we have the graph dataset, which consists of a set of named graphs and a default graph, and in which each named graph is a pair of a graph ID and a graph, and the default graph is a graph without an ID. As you can see in this example, we have a graph dataset where there are two named graphs, which are the events and the routes, and we have a one default graph, and it contains the metadata of two other named graphs. So this is one graph dataset, very typical dataset, graph dataset. So we have the definition of a graph dataset. It is a pair of GD and N, where GD is a default graph and N is a empty set or a set of named graphs. And each named graph must have a unique name in the set. Okay, so we move to the section 6. I'm gonna talk about other kind of graph data model and graph store. So basically, there are a lot more of other type graph data models because a knowledge graph can adopt any such graph data model based on node and edge. So that means that there are just small difference. It can lead to another type of graph data models. For example, we have complex nodes that may contain individual edges, or we can have the nested graph, sometimes called the hypernodes. But in this book, in this knowledge graphs book, we mostly just consider about the directed as labeled graphs, and it will be preferred to be discussed all over the later chapter of the book. So about the graph stores, the directed as labeled graphs can be stored in a relational database, or it can be stored in custom, sometimes called the native storage techniques, and they have also been developed for a variety of graph models. And a number of systems further allow for distributing graphs over multiple machines based on popular NoSQL stores. So this is the end of my section. So next will be represented by noun function. Thank you.
Hi everyone, I will walk you through section 2 of chapter 2. In this section, we will discuss querying in knowledge graph. I will introduce you about querying patterns and querying interface. Uh, First, Firstly, I'm going to talk about querying patterns. We will discuss um, about three types of patterns: basic graph patterns, complex graph patterns, and navigational graph pattern. A number of languages have been proposed for querying graphs, including the SPARQL query language for RDF graphs and Cypher for querying property graphs. Underlying this query language are some common primitives, including basic graph patterns, relational operator, path expressions, and more besides. We now describe this core feature for querying graph. In turn, start with basic graph patterns. At the core of every struct query language for graphs lie basic graph patterns, which follow the same model as the data graph being queried, additionally allowing variables as terms in basic graph patterns are thus divided into constants, such as article or value, and variables which we prefix with question marks, such as question mark event or question mark real. Um, the main idea of basic graph patterns or basic graph pattern is then evaluated against the data graph by generating mappings from the variables of the graph pattern to constants in the data graph, such that the image of the graph pattern under the map, replacing variables with the assigned constants, is contained within the data graph. Mm, we will have an example of a basic graph pattern. Looking for the venues of food festivals along with the possible mapping generated by the graph pattern against the data graph. You can see we have a directed edge labeled graph describing events and their venues on the right side. In this example, we have three constants: food festivals, time and venue, and we have three variable uh, question mark EV and question mark V and 1 and question mark V and 2. Basic graph pattern is then evaluated against the data graph by generating mappings from the variables of the data variable of the graph patterns to constants in the data graph, such that the image of the graph pattern under the mapping, replacing variables with the assigned constants, is contained within the data graph. We will have result like this. Um, we formalize basic graph patterns first for directed edge label graph and subsequently for property graphs. For this definition, we introduce a categorically infinite infin, a finite set of variable var. A con is the set of constants. A set A, a set var, intersection set con is an empty set, and terms is a set that is the result after the con set union var set. We define a basic directed edge label graph pattern as a tuple Q uh, equal V tuple of VEL, where V is a subset of term, V is a set of no terms, L is a subset of term, and L is a set of edge terms. E is a subset of V multiplied by L multiplied by V. E is a set of H. It is the triple patterns. Uh, now with the now next we define a basic property graph pattern as a tuple Q equal tuple of VELP UELP, where V is a subset of term, V is a set of node ID terms, E is a subset of term, and is a set of HID terms, L is a subset of term, and L is a set of label terms. P is a set of property terms, and U is a set of value terms. E is maps an HID term to a pair of node ID terms. E um, is map a node or HID term to a set of label terms. P maps a node or HID term to set of pairs of property value terms. And now, secondly, I will walk you through the complex graph pattern. In fact, a basic graph pattern transforms an input graph into a table of results, as you can see uh, in this image. So, the main idea of complex graph pattern uh, is using the relational al algebra to combine and or transform such table thus forming more complex queries from one or more graph patterns. Recall that the relational algebra consists of unary operators that accept one input table and binary operators that accept two input table. Uh, Basic graph patterns can then be expressed in a subset of relational algebra, assuming, for example, a single ternary relation GSBO re- representing a graph, a table Z with three columns SPO. Complex complex graph patterns are defined recursively as follows: if Q is a basic graph pattern, then Q is a complex graph pattern. And if Q is a complex graph pattern, and then V is a subset of var Q, then PVQ is a complex graph pattern. If Q is a complex graph pattern and R is a selection condition with Boolean or Boolean and equality connectives, then PVQ is a complex graph pattern. And finally, if both Q1 and Q2 are complex graph patterns, then Q1 join Q2 or Q1 union Q2 or Q1 difference by Q2 or Q1 minus by Q2 are also complex graph patterns. Um, and we have an example. We are going to look for food festival or drink festival not held in Santiago. Option, Optionally return their start date and name where available. As you can see, uh, Q1 we will find event Thai food festival, and Q2 we will find event Thai touring festival. With Q3 we will find venue in the Santiago City, and then uh, find the event in this venue. And then finally we will find start date of event in Q4, and in Q5 we will find name of event, and then finally we union Q1 and Q2. This means we will find event type, food festival and drink festival. After that we minus Q3, mean we minus event in Santiago, and then we join with Q4 to find to have a start date of event, and we join with Q5 to have a name of event. And the final graph pattern we will talk about is a navigational graph pattern. A, a key feature that distinguishes graph query languages is the ability to include path expression in query. A path expression R is a regular expression that allows for matching arbitrary length paths between two nodes using a regular path query. X R Y, where x and y can be variables or constants, or even the same term. The base path expression is where R is a constant, an edge label. Furthermore, furthermore, if R is a path expression, then R clean star 0 or more is also a path expression. Finally, if R1 and R2 are path expression, then uh, R1 disjunctions R2 and R1 concatenation R2 are also path expression. Regular path queries can then be used in basic graph pattern to express navigational graph pattern. Furthermore, when regular path queries and graph patterns are combined with operators such as projection, selection, union, difference, and optional, the result is known as as a complex navigational graph pattern. For example, we have a query search for food festival in city reachable recursively from a recur by bus or flight. As you can see, we have a directed edge label graph describing event and their venue on the right side. And so in this figure, which illustrate a query searching for food festival in city reachable from Eureka by bus and fly, we have the result like this. Mm, we first define path expression and regular path query. Path expression is a constant. H label C is a path expression. Furthermore, if R R1 and R2 are path expression, then R inverse or R clean star are path expression. Um, R1 disjunction, R2 and R1 concatenation, R2 are path expression. A regular path query uh, a regular path query is a triple X R Y where X and Y is an is element is are elements of a con union var and R is a path expression. mm, Navigational graph pattern. If Q is a basic graph pattern, then Q is a navigational graph pattern. If Q is a navigational graph pattern and XRY is a regular path query, then Q join tuple of XRY is a navigational graph pattern. And this is all about querying graph pattern, and then now I will move on querying interface. In fact, knowledge graphs are often queried by non-expert users who may not be able to express their information needs in terms of a particular graph query language. So different types of interface have thus been proposed in order to assist user in querying data graphs. Such interface may support, for example, the following: uh, faceted browsing, query building, query by example, and question answering. Firstly, we are going to talk about faceted browsing. User Users start by specifying a simple search such as a keyword search, a type of node like food festival or possibility are the kinds of search. They are then presented with a set of matching results and a set of facets, which are typically attributes, for example, value or and values, for example, Santa Lucia, present in the current result set. Selecting a value for a facet restricts the current results set to include only results with the indicated value. This selection process can be applied iteratively to restrict results per multiple phases. Often the phases criteria are translated into and evaluated as graph queries. Uh, though relatively intuitive for user, such a system typically support uh, acyclic queries that generates lists of results analogous to graph queries that process a single variable and rarely support more expressive queries. Here are some examples of uh, faceted, faceted, faceted browsing system for graph. Secondly, with query building, users are provided with a form of graphical interface that can be used to specify a graph query without needing to understand the syntax of a specific query language. Such query builder allow for incrementally adding nodes and edge to the query assisted by features such as auto-completion, previewing intermediate results, and graph navigation. Uh, Query builders typically allow for express query equivalent to cyclic basic graph patterns, but may not support more expressive feature and feature of query language as described herein. Here are some examples of graph by query builder system. Thirdly, I will introduce you to the query by example interface. User provide example of positive and sometimes negative uh, answer to their query. For example, they may provide as positive examples the nodes Eureka, Santiago, and Vandenberg, as and as a negative example, the nodes Chile and Lima, where the system will then reverse engineer to query that return positive examples but not negative examples. In this case, the query proposed may return nodes of Thai city whose country is Chile. Query by example system typically support basic graph patterns and may not support more aggressive, expressive query features. Um, they are useful in cases where users have example of what they are looking for, but are not necessarily sure of the query they need to retrieve similar examples. Here are some examples of query by example system. And finally, I'm going to talk about question answering interface. You Users express their queries as questions in natural language. For example, they might ask what food festival will be held in Africa. The question answering system will then generate answer from the graph based on its best interpretation of the question. Here are some example of question answering system. We identify three types of question answering system. Navigational A navigation-based system identify any node from the graph that are mentioned in the query, and then attempt to navigate edge from those nodes whose label best match the question. For example, they may match the nodes "food festival" and "Africa" in the graph based on the question, and from there try to navigate edge in the graph whose label match the question in order to find answer. A temporal-based system rather presuppose a fixed list of question template expressed in the query language, with placeholder variable that will be replaced with entity nodes detected in the question. Mm, a template match for the previous example may be of the from what is will be how in y. And finally, translation-based system attempt to translate the question into a query in the structured query language using typically neural machine translation techniques. The latter two type of question answering system can actually return a graph query that explains the answer generated. Question answering systems are often very intuitive to use, but may not always return correct results, particularly when considering complex question and query. And and that is my our presentation. Thank you for listening.